7:20 in the evening Eastern Time. In a data hall in Northern Virginia, multiple chiller units fail at the same second. 28 minutes later, in a Coinbase office in San Francisco, one of the on-call engineers is looking at a graph that should not exist. Bitcoin is fine. Ethereum is fine, but her company's trading engine is dropping orders on the floor. She refreshes the internal dashboard. Red. She pings the on-call. No reply. This is the story of how one building in a small town in Virginia became the internet's single point of failure, and how, on the 7th of May, it failed. It failed because of a building. That is the part nobody wanted to say out loud. The building is US East 1. Officially, it is not one building. It is a cluster of data centers in Loudoun County, Virginia that Amazon Web Services groups together and calls one region. But when the trade press writes US East 1, they mean one specific piece of physical infrastructure. And every engineer in America knows what that piece of infrastructure does. It hosts about 40% of AWS's global compute. AWS runs about 30% of the public internet. This one building matters more to the working internet than most countries do. The independent network observers at Thousand Eyes tracked the ripples that morning. They saw services degrade in places that had nothing to do with Amazon. Payment terminals stalled. Airline check-in kiosks slowed. Streaming platforms hiccuped on the East Coast for reasons their engineers could not explain from their own dashboards. And that is when you realize the problem. It was not just Coinbase that went down. Coinbase was the first symptom of something much older. This building had been trying to fail for years. To understand why one building would try to fail for years, you have to understand why every meaningful piece of software in America ended up inside it in the first place. The story starts in 2006. AWS launched with one region in Virginia. There was no US West. There was no AU Central. If you wanted a cloud, that was your cloud. That default never went away. Even after AWS added more regions, developers kept typing US East 1 out of habit. Documentation examples used it. Tutorials assumed it. New teams inherited it before they thought about it. The AWS commentator Corey Quinn has spent a decade documenting why this was not just habit. Companies signed multi-year discount contracts tied to the region. Leaving meant throwing away money already spent. Quinn's newsletter has for years called this pattern the tax on leaving. Meanwhile, in a small town in Northern Virginia, the buildings kept going up. The public planning documents at Loudoun County are a strange kind of archive. Nobody in tech media reads them, but if you sit down with the last 20 years of filings, you can watch a small county quietly become the most important piece of infrastructure in the American internet. By 2025, Loudoun County had more data center capacity than the entire country of Ireland. Dominion Energy filed with the State Utility Commission that its Loudoun load had grown 400% in a decade. The transmission grid could barely keep up. None of this was hidden. It was just distributed across 3 government websites nobody was reading together. The industry hadn't chosen US East 1. It had inherited it, and the inheritance came with a physical footprint that had grown load-bearing for the entire internet without anyone ever voting on it. Load-bearing infrastructure has to be cooled, and cooling, it turns out, is the part of a data center that nobody talks about until it stops. The Uptime Institute tracks the causes of major data center outages every year. Their most recent annual report puts cooling failures at close to a third of all serious incidents. Not software, not networking, the air conditioning. Inside a hyperscale data center, servers sit in rows of black metal cabinets, running as hot as they can. Cold air comes from industrial fridges the size of cars, dozens of them in each hall. They pull hot air out, chill it against water loops that run to cooling towers on the roof and push it back. If the outside cooling stops, the whole chain stops and the racks overheat in minutes. The engineering blog at SingleStore wrote a careful breakdown of what this actually looks like when it does. When the racks slow down under heat, transactions slow with them. Every failed request tries again at the same time, cascading into a wall of retries. And the backup plan, failing over to a second region, assumes the second region has capacity. If everyone in US East 1 fails over to US East 2 at the same second, US East 2 runs out of headroom in minutes. There is a stranger version of this problem, and Coinbase's own postmortem would eventually put it into public writing. Their matching engine, the piece of software that decides which trade fills at which price, runs on a small cluster of servers that vote among themselves. 5 servers. If 3 agree, the market moves. If fewer than 3 agree, the market stops. And they wrote why they put all 5 servers in the same physical room. A fair market runs on speed. The vote between the 5 servers has to happen thousands of times a second. Move even one server to a different building, and the trip time for the vote gets long enough that the market becomes unfair. The closer server sees the trade first. So the 5 servers sit in the same room by design. They were not warned into this. They chose it. Every serious trading engine on US East 1 has made the same choice for the same reason. This is what a single point of failure looks like when the point is a physical machine. It is not one wire. It is one building's ability to reject heat to the sky, and every serious engineering team on it has made a bet that the sky will hold. On May the 7th, at 7:20 in the evening Eastern Time, one building in Ashburn stopped rejecting heat to the sky. Coinbase's own postmortem names the mechanism directly. Multiple chiller units failed simultaneously in a single data hall inside AWS's US East 1 region, a specific wing of the building AWS calls Availability Zone Use 1AZ4, one of the region's independent power and cooling sections. The cooling loss triggered a thermal safety shutdown of the affected racks. That was the language of a public company admitting fault in its own words, days before AWS wrote anything for the record. AWS's own post-event summary eventually confirmed it, a thermal event, resulting in a loss of power. Their own page listed 9 affected services and named the wing Use1AZ4, which is what Coinbase had already written days before. The registers, Simon Sharwood, filed a version with less legal review. He named the exact wing, connected the cooling event to what actually broke, Amazon's virtual servers and storage drives, going dark inside that one section of the building. He also connected it to the older reputation the region had carried for years. Network World's Jana Swain wrote the deep technical version a few days later. The full 28-hour recovery timeline. The observation that older region cooling designs were not built for the thermal density of the AI era, and IT pros Emma Woollacott mapped which services degraded downstream Elastic, load balancing, Kubernetes, Elasticache, Redshift, OpenSearch, the plumbing under half of the internet, all of it downstream of one data hall. Data center knowledge put the incident in context. This kind of cooling failure is not rare, it is a modal failure. The Uptime Institute's data confirms it. Every hyperscaler loses a building this way every few years. What makes US East 1 different is what US East 1 carries, and what US East 1 carries starts to show up in the Coinbase postmortem itself, minute by minute. 7:20 p.m. Eastern, the chillers fail. 7:48 p.m. Eastern, 28 minutes later, nearly all trading on Coinbase halts. At 9:29 p.m. Eastern, AWS reaches into the physical room and shuts down the servers overheating inside it. 3 of the 5 voting servers in Coinbase's matching engine go dark at the same second. Fewer than 3 left standing. The market stops. Recovery is not a switch. Coinbase engineers ship an emergency code change during the incident, right there in the middle of the outage, to fix an assumption they had never questioned. The old code refused to start unless it could see all 5 voting servers by name. The new code accepts starting with the 3 that are still alive. They stand up new servers in a different physical room. They restore a working vote at 12:06 a.m. Eastern. They do not reopen the market until 3:49 a.m. Eastern, almost 4 more hours, because underneath the matching engine, another AWS product is failing silently. It is a message pipe. Every price update, every fee calculation, every downstream ping travels through it. When one section of the pipe breaks, an automatic switch is supposed to route traffic through another section. The automatic switch is itself broken. 2 of Coinbase's pipes are stuck in what AWS's own dashboard calls a healing state. Nothing is being carried. The fee service depends on the pipe. Quoting depends on the fee service. So most Coinbase customers experience this outage not as a broken pipe. They experience it as a broken trade. FanDuel goes down during Game 2 of Lakers Thunder. CME data feeds go stale. The independent monitors at Statusgator register more than 150 cloud services disrupted at the same hour. 20 hours. 8 hours of full disruption, and another 12 for the remaining system queues to drain. 20 hours during which one physical chiller in a small town in Virginia decided who got to trade Bitcoin. Who got to trade Bitcoin turns out to be a question that has been asked before. This was not the first time AWS had done this in this exact region. In March of 2017, an engineer inside AWS's S3 storage team ran a command with a typo, and the same building went dark for 4 hours. Half the internet at the time went with it. AWS wrote a careful post-event summary. The industry read it, said the right things, stayed on US East 1. In December of the year 2021, the region failed again. A different mechanism, same building. AWS wrote another post-event summary. The industry read that one too, and stayed on US East 1. This is the pattern. It has been the pattern for a decade. Amazon's own 10Q filing to the Securities and Exchange Commission has, buried in the risk factors, a section with a heading their lawyers wrote themselves. We face risks related to system interruption and lack of redundancy. The paragraph underneath lists the causes: natural disasters, extreme weather, energy shortages. Their lawyers write about it in clinical language that investors have been paid to ignore for years. That risk is not new. That risk is not surprising to anyone. It is documented in a public filing every quarter. And when this same building fails, as it just has again, the pattern completes itself. Coinbase writes a postmortem, AWS writes a post-event summary, the industry reads them, and every serious engineering team stays on US East 1 because they had a reason to be there before the incident, and none of those reasons have changed. Staying on US East 1 is what the industry is going to keep doing. AWS's post-event summary promised the usual mitigations: improved sensors, better runbooks, faster failover. These promises are indistinguishable from the promises made in 2017 and 2021. The AWS Chief Technology Officer Werner Vogels has spent his career saying a specific phrase: everything fails all the time. He said it in blog posts, he said it in keynotes, it became a shirt. He was right about the thing that fails. He was wrong about the number of times most companies have permission to fail with it. If your entire industry runs on one physical location, then everything fails becomes a promise about your customers, not your engineering. There is a version of the internet, one that Facebook briefly demonstrated in the outage of 2021, where a single physical thing takes the whole system down. We are supposed to have moved past that version. The May 7th event says we did not. The closing line of Coinbase's postmortem reads like this: their standard for being available, they said, does not depend on whether AWS has an outage. It rests entirely on whether they have built systems resilient enough to withstand one. That is a sentence public companies almost never write. It is also the correct standard, and it is a standard that requires a working alternative to US East 1, an alternative that has not been built. The Public Planning Office in Loudoun County keeps filing paperwork. Dominion Energy keeps filing load projections. The transmission grid keeps growing, and every serious engineering team in America keeps typing US East 1 out of habit, because the economics have not changed and the alternative has not been built. The next chiller will fail too. The paperwork is already in. The paperwork is always already in. Somebody just has to read it before the next chiller fails. This has been examined. Subscribe for the next one.